So you can use it to detect pretty much anything. I think this is kind of interesting, I think, because if you're in the DEA and you get a sample of opium, well, you could run its chromatogram and see where it came from, as long as you have samples from all around the world. Okay. Arson, a lot of uses. Quantitative and qualitative analyses. Okay, gas chromatography. GC. What is the mobile phase, Kat? What is the mobile phase? Yeah, we're doing GC. So it's not a liquid, it's a gas. A gas is the mobile phase. Upstairs, the whole world is moving from helium, if it hasn't moved already, to explosive hydrogen as the mobile phase. And it's just a fact of life. And hydrogen's much more abundant. Okay. Almost all chromatography performed today utilizes capillary columns. At the head of the column, when doing GC, the sample is, John? Remember what the mobile phase is? It's got to be vaporized, right? Okay. GC instrument flow diagram. Casey, perhaps you recognize the little green box on the GC. What was that? That's where you inject. That's the green nut where you inject, right? So that's why I made it green. It's the only thing I really recognize. Well, you might recognize this guy, the Mickey Mouse looking thing. Kimberly, you recognize what that is? All right. There are some copper lines. All right. All this stuff is connected. There's numbers on here. This was our big gas cylinders. Right? And if you did buy one of helium, it would be roughly $900 to $1,000. Hydrogen's only a couple hundred. So, and this stuff has to be 99, they call it 5-9er gas. 99.999% clean. And then it's run through a filter after that too. And the big one remove is oxygen. It just damages the column. Anyway, so we're going to go from there into our machine, right? And we'll probably get that mobile phase into the inlet where you're injecting stuff. So you inject stuff into here, right? That's that green nut. This whole little box, I think you can call it the inlet. Right, that's where everything's going to get vaporized. Then it runs through a column, really long column, probably like 30 to 60 meters long. Then it ends up going to the detector. So if the column does its job, Miriam, what would be eluting from the end if the column does its job? Well, yeah, the gas, the mobile phase, was always coming out, but you shoot this mixture, and then the pure parts or pure components will be coming out if the column does its job. They'll be really dilute, remember, but it'll work. And then everything is connected to the, right? All the electronics are going to the computer. What's the dashed line mean? All this stuff is inside here's what it looks like inside, but all this stuff is inside so it's an O. Use it to control the temperature. Oven. All that stuff is inside an oven. And it's an oven where you not only want to control the temperature to, very, very finely, but you want to adjust the temperature really quickly. So you see, can you recognize what's in the back? If you popped open that door, what's that big thing in the back? See, here's my column. There's my column. Here's my inlet. Here's my detector. What's this big thing right here in the middle? A big fan. Right, so you can remove the air, and you can change the temperature and adjust it really quickly on the fly. Okay. Common GC detector, a flame ionization detector. Okay. How does it work? Well, so this is the guy that's on the very end of the column, right? He's the, up here, he's the detector. Over here, if you want to see that, the column's running into him. And that's where we're at. And it's an extremely hot flame. It's a flame that usually when you burn stuff, you know, you get what and what? You burn stuff. You make a campfire. You get what when you burn stuff? You get, well, yeah, in the end you get ash. But what gases do you get? When you throw anything in there, paper, and you burn it. You get CO2 and water, right? You get water. If you burn things at even higher temperatures, you start getting some different, combustion's really complicated. But if you forget all the complication and just make it extremely, extremely hot, make it a torch in there with all these high, like hydrogen, it's a hydrogen flame. It's extremely hot in there, high pressure, and they're just shooting it out of there. They're making a really nice torch, extremely high temp. Things burn completely to their carbon atoms, but more so the carbon ions. So this guy he's just making carbon ions is all. And then you can see that, oh, not carbon plus. The reason why I see it's not plus, because look at the voltage. It has to be carbon negatives, right? These little ions of carbon, they're going to be negative. They're going to hit the sides. Right? Once they're generated, they're going to hit the sides. Because he's positive, they're negative. Generate a little bit of current. So really all an FID is a what counter? Yeah, what type of ion though? Yeah, only carbon. Carbon is it. Everything else you can't detect. You blow sulfur through there, can't detect it. Because the only thing it's going to get, the only thing it generates are these carbon ions. It's the only thing it can generate. So oxygen, it can't see. You can't see a lot of that kind of stuff. So it's called literally a carbon counter. And the more carbons there are in this thing coming off the column, the bigger your signals are going to be. So Jamesa, what would be something that this FID couldn't detect? Well, it can't detect metals. But metals can't be vaporized in the first place. Any gas that doesn't have carbon. Okay. But well, could you name one? Anybody name one? All right. Nitrogen. It couldn't see nitrogen. What else couldn't it see? What's that? Oxygen. Right. There was a chemical company that had these big barrels. They buy stuff. I don't know, the toothpaste manufacturer. I forget what it was. But their barrels were getting bigger and bigger and bigger. They go out there and they take a little bit of the gas, and all they're worried about is if it was explosive or not. And sure enough, you put catch a little bit of the gas, put a flame on it. Uh-oh. So now they're getting scared. So they put it on this machine. I'm trying to figure out, what is it? They don't get any peaks. That means it had to be what? Something that doesn't have carbon and it's explosive. Hydrogen. Right? Okay. Using a C18 column. Now we're going to talk about what the C18 part means later. All right, we'll talk. Don't worry about this. We'll talk about that later. Okay. But using a capillary column, a sample of gasoline was injected on a gas chromatograph. And here's the temperature of the inlet. And again, its purpose is just to vaporize it. Right, yeah. Now, you don't want it to be too high, because if it actually decomposes stuff, well, then you're going to be analyzing the decomposition products of gasoline and not gasoline, right? So you don't want it to be too high. But 250 works. The oven was set at 145 degrees. So they hire you to run this. You really loved it, because this guy comes off at like 55 minutes. So once you get all this stuff, and then you got a long time. You get a long lunch. You can play around on Facebook. You can do all this stuff. But your bosses don't like it. What are they going to have you do? This is a hard reach. With liquid chromatography, when they say chromatography, you're just moving the peaks around. You're trying to get pure. That's the big goal. Get pretty peaks, but have them all completely isolated. And you have all these peaks nice and isolated. It looks great. Except, look at all the time you're wasting and mobile phase and everything. Well, it's gas. Who really cares? But you still got to pay for it. But it's the time that's the dude you're paying. If it was liquid chromatography, you just change the mobile phase so that the stuff dissolves better, right? And it'll go faster. And you can do that. These machines will let you change the mobile phase. But in this guy, you can't change the mobile phase. You can't change the column. Well, your thing's in there. Change the temperature. That's what you do. Perfect. Okay, we're getting there. So, after about everything is nice, hunky, and dory, what is that, around 7 minutes or so? What are they going to have you do? Make the temperature really high or make the temperature really low of this oven? It's going to be really high. And you're going to see why better in a little bit with how things work. But crank up that temperature. After, what is that, 7 minutes or so. Get that puppy out of there. Get him to elute. Okay. He's the only thing remaining. So when using capillary columns, the analyte, what we're after, it's partitioned. What's partitioned mean? Distributed. Good. Did you hear Nyla? I think she said distributed, didn't you? Between the mobile phase and a liquid phase that is immobilized on the walls of the capillary column. Therefore, this type of chromatography is referred to as probably gas liquid chromatography. Yeah. So when you have these columns that we're drawing, right, there's actually a liquid in there along the walls of the column. So these capillary columns in gas chromatography, there's a couple types. Now when they say column wall, what is that? What is that physically made out of? Can't be plastic, because plastic, like they're cranking up the temperature and all this stuff, it would melt on you. It's glass. It's glass. That column wall is glass. Right. Okay. So let's see. And then they have this liquid phase in there. So this is definitely the most common one. This is your gas liquid chromatography. And then they have a solid support. So now you have these solid stuff in there. You still have a liquid phase on the solid. Or you just have the solid stuck in there. Okay, so I don't know how they do it. I mean, imagine a capillary column, and how do they get a liquid in there? Or solid stuff? Yeah, you want the big hole in the middle, right, for the mobile phase to flow through? There's a lot of engineering in that. Okay. So here it is. Here's a capillary column. And I put it in a Ziploc bag because it is glass, but it bends, right? And if you broke it, I mean, it could shoot in your eye or something, so that's why it's in a bag. But does glass bend? You take that window, right? How the heck can glass bend? Yeah, but look at this guy. He's passing around. He's room temperature. The only way is to make it very, very, very pure. If there are no impurities in that glass, it will bend. It will. I mean, it's proof right there. Okay. But what color is glass? Make glass really, 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 really pure. What color should it be? It should be colorless, right? I mean, it's glass. So, why is this thing that's going around? What color is it, Jamesa? It's like a gold orange thing, right? So it's right here. There it is. It's coated. It's coated with this. And the reason why is because that is really, really pure. What is glass? Silica SiO2, right? It's crystal, right? And if you touch it, it gets really reactive with your fingers. It's really reactive. So you got to protect it from like the oxygen in the air and other things. So that's what the polyimide coating does. Is it just protects the glass. Because if you scrape off a little bit of it, and then you try to bend that part where you scraped, it's going to get brittle because it's not pure anymore. It reacted with whatever you scraped it with or with the air. Okay. So here's a cross-sectional diagram of a capillary column. So this outer dark thing is probably the what? Polyimide coating. Polyimide coating. And then going a little bit further, the next layer is probably the glass. The glass. Then, someone said it, that liquid.
Is it really liquidy or is it more like jelly?
It's liquid. It's oh yeah, what exactly its consistency is, I don't know. But I think it's so thin that it adheres. And it doesn't drip out or anything. It's so thin. It's like a real smearing going on there. And I bet you it is really thick because we're talking about some really, really organic stuff. Very fatty-like. Okay, it's going to be the most common that you're going to see in a little bit. So if you take a look at what's going on inside a capillary column, okay, the below illustration of the molecular action. So here it is. We really have two bands. I mean, here's a compound, the red dots and the blue triangles. So they're nice and separated, but notice they're traveling in this direction, right, through the column. But it's kind of lacking because no dynamic equilibrium is shown to exist between the what and what phases. The mobile and stationary. These guys are continually going in and out as they pass through, right? And then when it's in the stationary phase, when it's dissolved into that liquid phase, it's not going to move, right? It's retained. Only when it goes into the mobile phase, just like liquid chromatography, that's when it's going to move. Okay. Okay. In the below illustration, Pablo, which compound has a higher affinity for the stationary phase? Which would you say?
The red one?
Yeah, the red one. Do you agree? Because look how much more the red one is. His concentration is a lot higher in the stationary phase. Yeah, so the technical jargon is he has a higher affinity for the stationary phase. He dissolves better. Like dissolves like. So that means the red one must be more chemically similar to the stationary phase than the blue triangles, right? Because like dissolves like. Okay. Which will elute first? Yeah, the blue triangles. They're already winning, right? But yeah, there's more of them in the stationary. Sorry, there's more of them in the mobile phase. They're flying through there faster. It's more unlike stationary phase. And this really isn't that big a deal. It's just showing that, look at the difference between, if you have a column, right, packed with a solid material versus the column that, capillary column, right? I mean, which one would you buy? You'd buy the capillary column, right? So the peaks are sharper. It's everything about it's better. So no one even uses packed columns anymore, but it's still within people's memory, so you still hear about it, I guess. Okay. And then, Natalie, what's going on here? What's changing? And going from one picture to another picture to another picture. They're changing the definitely the bands are changing. These bandwidths are changing. But to get those bandwidths to change like that, they're changing the way. They're injecting the same thing again and again and again. They're changing the temperature, right? Does it make sense that this one 75, 110, 130. Does it make sense? Thinking about this? Can you tie in those two thoughts?
Did you say
This?
it gets hotter as you
So these are the oven temperatures, and they're just keeping it there. So at 75, right, things are taking a while, and they're fatter. To the other extreme, make it really hot, man, everything's coming out at once. They're not even resolved. How does that correlate with this? It has to, somehow. If you crank up the temperature, how does that affect this? That- Let's say that's 75, and let's say this guy is, what was the other one? 100 and 100, 110, 130. Right? Now this doesn't change. The flow of the mobile phase doesn't change. He's the same. It's the same stationary phase. It's the same compounds. But they're just, you're getting it. They're, ooh, the time they spend in the which phase changes a lot. Stationary phase. Look how hot they are. Why would they dissolve when they're flying through? Right? They have so much energy. They're not gonna. Yeah, they will interact with the stationary phase, but not much. Especially when you make it extremely hot. They don't even interact hardly at all with the stationary phase. They're so hot. Everything is in the mobile phase, just flying right on through. Okay. So that's the power that you have with gas chromatography, and that's the only power you have, is to change the temperature. That's all you can do. When you try to do chromatography, to try to separate compounds out, the only thing you can do is change the temperature. Okay. So let's take a look at this inlet and its parts. Okay. Now, this guy that's our green nut. Okay. And this one right here, this guy, he's our rubber septum. And it's right here. Okay. I don't know if you've done GC with organic and they had you change the septum. You know, and I've got this little manual up there that says change the septum if you're the third user or something like that. And that's what this orange thinger is. And then also in here is a piece of glass that's slid in there. That's the glass liner. So that's what's being passed around. And the reason why you want the glass liner in there is especially for students doing research. And okay, Nyla, you use the HPLC for your research project. Oh, but I want to use the GCMS. So she runs over there and shoots her, I don't know, she wants to compare Coca-Cola made in Mexico with Coca-Cola made in San Antonio. So she shoots her stuff in here, right? What happens with sugar when it's really, really hot? It melts, it sticks, it caramelizes, it just decomposes. Oh my gosh, imagine trying to clean that up in this little inlet. That's why you pop out that glass liner and put in a new one. So that's why this guy's there, to help keep things clean. Makes it a lot easier. Okay. Now, everything has to end up on the column sooner or later. So that's what that is. That's our column. Okay. We have to shoot our mobile phase in here somewhere. Well, that'll be that mobile phase inlet. Okay. Now, think about it, something else that makes sense. The carbon dioxide one. We were having trouble. I think it's because of the dang septum or what. I'm not sure. There's something going on with our inlet that's messing things up with one group. With another group, they got hardly any signal. So I think, again, it's something was going on with the inlet. We messed up. I think I had to replace that septum or something. Anyway, with one group, we weren't getting hardly any signal at all. So I changed what's called the split ratio. Because if you want to make this thing as sensitive as possible, everything you inject, have it go down here. That's called splitless. That's as sensitive as you can get. Everything that you inject goes onto the column. But when everything's running right, if you take your auto exhaust sample, inject only 1 microliter. That's all we're doing. 1 microliter in here. It saturates the detector. And I don't know, the group that was with me, they saw it. It was this big. We had to wait, I don't know how long for this big peak to finally get out of there, right? So that was when we did it in the splitless mode. So we said, well, forget that. This is not working. We don't want to do that again. So we went to split mode. And we split it, I don't know, like 50 to 1 or something. The computer does it all. But we said, okay, let's split it at this ratio. 50 parts are going to go out the split outlet, and 1 part will go down the column. So it dilutes your sample. So you don't have to do it yourself. The instrument will do it. That's kind of nice. Okay. So that's our GC splitless injector. There's 1 part left. This thing. The only way that you can relate to why it's there is if you've gone to Walmart or Sam's and you really like the smell of tires. I love the smell of tires, and I don't know why. But Sam's is really good about this. They have all those brand new tires out, and right? You ever smell tires? No? Well, if you like the smell of gasoline, you'll love the smell of tires. I like the smell of gasoline too. Anyway, rubber, you can't stop it. I mean, it's constantly kicking out gases. Rubber is. You just can't stop it. So, and this machine is so bloody sensitive that we have to and this is what's kind of weird to me, is that rubber septum up there. We don't have a better material than rubber that you can stick a needle through and keep it airtight? I guess not. When you think about it, I guess we don't. Because then you pop it out, it reseals itself. We don't have anything better than rubber. Since we don't, you have to constantly blow gas through there, blow mobile phase through there. So that's the septum purge outlet. Because if you don't, and you still can't get rid of it, when you saw a lot of noise in that noise is all signal from the rubber septum. It's a huge background. So you try to reduce it as much as you can by having a septum purge outlet. Okay. So there's 3 ways a sample can leave the inlet. You, Randy, you recognize what they are? Column. And the 2 outlets. Exactly. Yeah, the split and the septum purge. Sample overload. Last thing. Okay, what project do you want to do? There is a project that I'm looking at right now of doing. And the most expensive coffee in the world. Have you read this? Cat poop coffee. You probably know more about this than I do, because I just read about this 20, 30 minutes ago. Okay, what cat poop coffee is, now the article was wrong, and San Antonio Express News is wrong. They said that these cats, they go sniffing up the best coffee beans and they eat them, right? And then they poop them out and people clean them up and wash them and sell it. It's the most expensive coffee in the world. It's supposed to taste chocolatey or something. I don't know. Anyway, that's not how it works. How it works is, I don't know if it's a special cat or what. According to them, it is. I'm not. This is where my research is really going to, I think, kick in. Okay, so the cat ingests it, the CEVITE cat. Anyway, his enzymes in his gut start digesting the beans, and then the cat craps them out. Okay, so he can't digest them. You can't stop that digestion process, right? Some little interaction happens there, but that bean is so dang tough. They call it a violent eruption from the cat. I don't know why it would be violent, but anyway. So you get the violent eruption from the cat, and you clean them up really good, right? And then so there's some interaction between the enzymes, protease, and what's going on in there. So that's where I'm really getting interested, because I don't need to go digging cat shit, right? I can go talk to biology people, get some enzymes, make a little bath, dump some coffee beans in there. I've got, do I or do I not, the most expensive coffee beans in the world. If I do, I get all the patents. And maybe I'll hire you on when you graduate. Right? But how would I know I got where I need to go? Chromatography. I'm not going to drink this stuff. Why? Right? I'm going to chemically analyze it, see what peaks I need to get, see what I'm after. Okay, what I'm showing you this is, you need to inject this stuff onto the GC. And there's so many parameters. There's the temperature of the inlet. You don't want it to be too high, because I don't want my little coffee bean stuff to decompose on me. So, okay, fine. We'll set it, what temperature can you get it at? We'll set it there. But that's a parameter. Something needs to be dissolving this stuff, methanol, what? I don't know, you got to pick something. But all these things expand differently in different temperatures. You have a flow rate coming out of the column. You have a pressure of the inlet in the first place. I mean, come on, it's going to take forever just to figure out how to inject something, right? I mean, what temperature, what pressure, what flow rate, you let theory tell you. And that's what this flow calc thing is. You plug in your liner that you actually have, that you have in that machine, you plug it in here. So now the software knows how much volume you have to work with. You plug in your pressure, your temperature, the amount you want to inject, because maybe this stuff is extremely trace, and you want to inject the maximum amount you can. Well, you don't want to do what we had with the auto exhaust. Have these big fat peaks. It's not going to do you any good at all. You need sharp, pretty peaks. So how do you get it? As quick as possible. You start with something like this. And it tells you, okay, if I'm going to end up using methanol at this temperature, this pressure, I don't know, seems fine. How much can I inject? Right? Oh, what? That's too much, right? It looks like I'm getting worrisome around 866 microliters. The problem is the most friendly solvent around is water, but water expands big time, and that's the problem with water. It drops way down. 613. And temperature 175 really doesn't make sense. It's going to be more upwards of like 250. Those are more common injection temperatures. You got to go even lower then. Okay. Pressure. Yeah. I see that you just play around with it. As long as you're in green, you're good to go. Okay. So have a good weekend. Oh yeah, the exams.